So now we're going to talk about those different types of reactions that we were introduced to in the beginning of the chapter. We mentioned laundry detergent. Sodium carbonate that's present in the laundry detergent, and that's washing soda if you're interested. Washing soda is sodium carbonate. Sodium hydrogen carbonate is baking soda. So some of my friends, and I tried it too, I wasn't real happy with it. There's this, movement to make your own laundry detergent, save lots of money, right? I wasn't impressed. I tried it and things got very gray. You have to add sodium carbonate, washing soda, to your homemade detergent to get rid of the hardness in your water. So, because the sodium carbonate precipitates with the magnesium and the calcium. Remember, the carbonates were generally insoluble. So we throw carbonate in there to precipitate the magnesium and the calcium out so they can't react with the actual soap in our detergent. So precipitation reactions form a solid. The solid is called a precipitate because it precipitates. Here's an example. Here's the description in words. When a potassium iodide solution is mixed with a lead 2 nitrate solution, a brilliant yellow precipitate of PbI2 forms. Here's the balanced chemical equation, and here's the picture. So we have a clear liquid mixing with a clear liquid, and we get this bright yellow precipitate forming. It kind of seems like magic, but it's not magic. Potassium and iodide ions together are a soluble compound. Lead and nitrate ions are a soluble compound. But when these two mixtures come together, we get lead and iodide ions together, and they form an insoluble compound. And so they precipitate and make a solid. And again, when we see cloudiness like that, that's indication that this is a solid. It's just small particles. Yes?
I mean, because if it's doing that, it's liquid, right?
No, it isn't.
So as soon as it just turns hard in that shape?
It's like smoke. Smoke is actually solid particles. And you can't see through it because it's larger particles than the molecules of air. And they reflect and refract the light.
So if you touch it, it wouldn't feel solid?
It wouldn't feel solid. It's a lot like, think of silt from the bottom of the river. So if you get some sand and dirt and river water and you put it in a big clear container and you let it sit, all the silt and the sand will settle to the bottom, right? But then if you stir it up, what happens? That silt suspends in the water and it gets all cloudy and muddy looking. Does that mean it's a liquid? No, it's just little tiny particles. And when you stir them up, they're small enough that they can float up and float around for a little while, but then eventually they fall back down.
So it doesn't turn into a solid shape?
No, that is, I'm glad you asked that question. It will settle down, yes. If you leave that alone, it will settle and you'll end up with tiny particles of yellow solid on the bottom of the flask, and the rest of it will be clear. That's a really good question. If we mix potassium iodide and silver chloride, nothing seems to happen. Potassium with iodide is soluble, sodium with chloride is soluble. When we mix these two, we have a potential for an interaction between sodium and iodide and potassium and chloride. Both of those compounds are also soluble. And so it appears that nothing has happened. And indeed, there is no chemical reaction. There is a physical change, though, in that they are now mixed. So mixing is a physical change, but there's no chemical reaction because no solid was formed. The potassium ions and the sodium ions and the chloride ions, they're all just in solution still. Nothing has really happened to them except now that they're mixed up. So how do we predict whether a precipitation reaction is going to occur or not? Well, we have to understand that only insoluble compounds form precipitates. And we just went over the rules so we can predict whether something is soluble or not. So in a precipitation reaction, we've got two solutions containing soluble compounds. They combine and they form an insoluble compound. So we have to look at the potential products and identify if either or both of them is insoluble. So let's look at that first example in more detail. So here we've got potassium iodide. This is a soluble compound. And so the iodide ions and the potassium ions separate and they mix around and we've got this nice solution. Over here we've got lead and nitrate ions and they dissolve in water. Immediately after mixing, we still have these ions. But now, these are moving around. Actually, let's go back here. So I have a twisted chemistry land analogy for this. This is like people going to a party. And I've told you that the metals are men and the nonmetals are women, right? So here we have potassium and iodide. And they're going to the party together. And lead and nitrate are going to the party together. And what happens when they get to the party, initially, everybody's soluble, they're going to mingle. But as they're mingling, lead sees iodide for the first time. And the sparks fly, okay? These guys form an insoluble compound. And they're going to go off and find a quiet corner somewhere, and you're not going to see them for the rest of the party. They are insoluble. They are going to precipitate out, okay? And potassium and nitrate are like, I'm not really that attracted to anybody here, so I'm just going to mingle and have fun, right? So we've got potassium iodide and lead nitrate coming to the party. And then to predict the products, we're going to look at what are the possible combinations. Can't remember what the next slide is. So the possible combinations, I entered drawing mode and exited it. Come on. So Pb, 2+, and potassium. Potassium came with iodide and lead came with nitrate. And so we're looking for the combination that forms an insoluble compound. We know it's not lead with nitrate because in the beaker all by themselves they were soluble. And we know it's not potassium and iodide because they came together, but they were soluble. So we have to look at the swapping of partners and see if there's any chemistry between these people. So for the lead iodide and potassium nitrate, those are our possible products. And how do we know if one or both of those are insoluble? We look at the rules, the solubility rules. So if we look up iodide in that table, we find that iodide compounds are generally soluble, except iodide has a weakness for lead. When iodide gets with lead, they're off, making out in the back corner, right? Potassium and nitrate, potassium compounds are always soluble, nitrate compounds are always soluble. This compound is soluble. It's not going to precipitate. So this is our precipitate. So we look at the ions that came in and we look at the combinations that are possible. There's only going to be 2 possible new combinations. And this is the 2 couples come to the party and they swap partners. And then you're asking, are the sparks flying or not? So here's lead and iodide, and they found a couch on the back porch, and who knows what they're doing. And potassium and nitrate are still at the party mingling, okay? You'll remember that one. So writing formulas for these compounds. Writing equations. First you have to write the formulas for the compounds that are being mixed, the 2 reactants. And then below that, write the formulas of the ions. Pull them apart. Include the charges. This will be helpful. Then exchange anions, swap partners. Rewrite those formulas on the reactions. That should be the product side. How did I not see that before? Let's fix that. On the product side. And then use the solubility rules to see if you've got an insoluble compound. So let's do, oh, wait, there's more. What if both of them are soluble? Then there's no reaction. And you can write no reaction or even NR next to the arrow, and you're done with it. If one or both of them is insoluble, indicate that with your state symbols. Then balance the equation. Do not change the subscripts. It's really tempting because it would just be so easy, but you can't do it. Okay, let's do one example before we call it quits for today. Write an equation for the precipitation reaction that occurs, if any, when solutions of potassium hydroxide and nickel 2 bromide are mixed. So I need to first write the formulas for these compounds. So potassium hydroxide, and we're told that that is a solution, so it must be aqueous. Potassium hydroxide, I got that because potassium is K plus and hydroxide is OH minus. And when I put those two together, I've just got plus 1, minus 1. I just push them together and they're good. Then over here, nickel 2 bromide. Well, nickel 2 is Ni 2 plus, and bromide is Br minus. So those must go together as NiBr2. And that's a solution, so that's also aqueous. And then I'm going to have an arrow. What are the possible products? Well, that's swapping partners here. Potassium came in with hydroxide. Let's see how potassium and bromide get along. And then that leaves nickel and hydroxide to get to know each other. So I'm going to take those ions. It's really, really, really helpful to write these down here. Really, really, you need to do that. And over here, below where I'm going to write my products, I'm just going to write the ions again with their new partners. And I've got Ni 2 plus, and I'm running out of room, of course, and OH minus. Now, if you wrote Ni 2 plus with OH minus first and K plus with Br minus second, that doesn't matter. The order doesn't matter. What is important, though, is that you've got a plus and a minus, a plus and a minus. Okay, there's a guy and a girl, a guy and a girl. They came in that way, and they didn't change while they were at the party. Okay, it's not that kind of a party. So we've got plus and minus, because sometimes students will try to put K plus and Ni 2 plus together. Well, good luck getting those charges to add up to 0. It's not going to work. Opposites attract, okay? And this is no commentary on sexual orientation or anything, but just it's how the ions work. Opposites attract. So now that I have those ion formulas, I can put them together into compounds. So K plus, Br minus, I just need one of each. And I'm going to leave a little space here because I need to indicate if it's a solid or not. Ni 2 plus and OH minus. Seriously out of room here. And I'm going to have to put his state symbol above, I guess. It needs 2 hydroxides to balance the charge on the nickel. So I've got my formulas. Now I go to the solubility table. I look up potassium. Potassium's always soluble. No exceptions. So then the state symbol for potassium bromide is AQ. Then I look for nickel and hydroxide. I don't find nickel in the table, but I find hydroxide in the lower portion. Hydroxides are generally insoluble. There's a few exceptions. Nickel hydroxide is not one of them. So nickel hydroxide is a solid. If that had been aqueous, there would be no reaction. But because that one's a solid, there is a reaction. And then we have to balance the equation. So I'm going to look here. I've got 1 potassium and 1 potassium. This ion stayed together. It stayed intact. It just went with a different partner. So I can balance them as individual atoms if I want to, but I don't have to. I can balance it as a unit. So here I have 1 hydroxide ion, and over here I have 2 hydroxide ions. So that means that I want to put a 2 here. Well, that messed up the potassiums, so I'm going to put a 2, where am I? I get lost in my zoom here. So I need a 2 there. So now I've got 2 potassiums, 2 potassiums, 2 hydroxides, 2 hydroxides, 1 nickel, 1 nickel, 2 bromines, and 2 bromines. So there's my balanced chemical equation for the precipitation reaction. I'll see you on Thursday.